Hello everyone. Welcome back to our Toronto AI Robotics L seminar. Today we're glad to have Frederike Dümbgen to give a talk on towards globally optimal state estimation. Frederike Dümbgen is currently a postdoctoral researcher at the Robotics Institute of University of Toronto, working with Professor Tim Barfoot in the Autonomous Space Robotics Lab. She received her PhD with thesis entitled Blind as a Bat, Spatial Perception Without Sight in November 2021, under the advisors Professor Martin Wertley and Dr. Adam Schofield from the Laboratory of Audiovisual Communications in Computer Science at EPFL, Switzerland. Before that, she obtained her Bachelor of Science and Master of Science in Mechanical Engineering from EPFL in 2013 and 2016, respectively, with a minor in Computational Science and Engineering, and Master thesis at the Autonomous Instance Lab of ETH Zurich. Her research has ranged from novel localization methods, in particular acoustic, radio frequency, and ultra-wideband localization, to most recently globally optimal methods for robotics. So yeah, Frederike, we're all looking forward to your talk. The stage is yours.
Thank you so much. Thank you for the kind introduction, and also thank you for organizing this and for inviting me. Yeah, so I'm really excited to, for the first time actually, talk about our latest research, which is on towards globally optimal state estimation. And this is all collaboration with Connor Holmes from U of T and Professor Tim Barfoot. So I don't think I have to convince anyone here in the audience that a lot of robotics problems nowadays are solved or are stated as an optimization problem. If you think about state estimation on the left here, you typically want to find the best state given some measurements to, for instance, landmark points. In motion planning or in trajectory planning, you might be given like a start and an end point and a map, and you want to find the best obstacle or collision-free trajectory that combines them potentially under some like time optimality or cost optimality functions. And to the right here, we have inverse kinematics problems, or like more complicated planning problems where you have like, for instance, redundant robots, where often you will also pose this as an optimization problem. And here the particular thing is that you might often have multiple solutions that actually are the global optimum. And typically, what people use as solvers, this is probably a big oversimplification, but just like very broadly speaking, people use often gradient-based methods. So that's, for instance, Gauss-Newton or Levenberg-Marquardt for least squares problems, in particular nonlinear least squares problems, or sequential quadratic programming as soon as you add constraints. And on the other hand, you have kind of these sample-based methods where you, instead of using gradients and differentiating your model, you can try to approximate it with samples. So that's, for instance, Monte Carlo estimation methods like particle filters, or sample-based planners like BitStar, RRT-star, and sample-based MPC more recently. And what all of these methods have in common is that they're actually suboptimal, or that we only have guarantees that, for instance, the gradient-based methods are locally optimal. So they will find an optimum that is first-order optimal, but it might not be the global optimum. And similarly, for sample-based methods, we typically know that they're asymptotically optimal. So if you have infinitely many particles, then you will actually find the best solution, but that is only really true at the infinite, like as you go towards infinity with the number of samples. So we are kind of focusing on state estimation today, but I will give a little bit, I will try to keep everything relatively general so that hopefully it will kind of inspire you to see how to use these tools for your own research to reach global optimality also for other problems in robotics. All right, and why do we even care? Why is locally optimal sometimes not good enough? So I have this like simple state estimation problem. So this is a data set that was recorded by Abhishek Gudar and his colleagues also at U of T. And previously DSL, should say here. So here we have a drone that is flying in an arena, and it's measuring distances to fixed anchor points. So the crosses here are fixed anchors, and the drone is estimating its trajectory. And in black, you have the ground truth. In orange, you have what we're estimating. And this, what I'm showing here, is actually the best solution, the global minimum. But it turns out if you use a kind of unlucky initialization, then you might converge to something like shown here. So this is obviously very far from the certified global minimum. And this is really kind of could lead to very unstable behavior if you're using this in like a closed loop system, for instance. And if you're doing kind of motion tracking or a motion, MPC based on a state estimate like this, for instance. Now, maybe the listeners are thinking, okay, this is kind of a contrived example. Like what I've shown you is just kind of poor landmark placement. In fact, all the anchor points here are on the ceiling. So they're all in a plane that's like poor conditioning. But I want to argue that we can't always control this. If you think, for instance, when your anchor points or your map points are visual features, you might end up in a situation where you actually have only features on a wall, for instance, and that's typically leads to poor conditioning and then bad local minima. You might also say, well, clearly this right solution has like probably quite a bad cost, so I can just accept a solution only if it has a good objective value, but this is not true. In fact, local minima can be quite close in cost and still be very far from global minima in, for instance, the RMSE error. So in this particular case, for instance, the cost is almost the same. And I will show that a little bit more in detail later in the presentation. And finally, I think what's worked pretty well so far, and I mean, maybe the reason why local solvers are still used quite a lot is that you can sometimes, if you find a good initial estimate, then you can actually converge to the global minimum. But it is not always available, like we can't always do that. And still, even if you start from a good initial estimate, you don't have a guarantee that you're going to find the global minimum. So it's still, even then, it's still interesting to be able to certify that we do in fact have the global minimum, and we don't have to worry about being far in terms of the RMSE, for instance.
Sorry, Frederike, can I ask a question?
Yes, please. Please interrupt anytime. Yeah.
Perfect. So I guess this is a problem with nonlinear likelihood functions, right? Mm-hmm. So if we were to turn the optimization problem or the estimation problem in if you were to linearize it, let's say using Koopman operators, for example, that then we are dealing with a linear estimation problem, and then we don't have to worry about this, right?
Mm-hmm. Yeah, that's true. Yeah, that's a good point. So I'm kind of talking about like typically non-convex problems. Mm-hmm. It's true that if you can somehow lift your problem, like for Koopman operators, to like if you lift it high enough so that it becomes a linear problem, and you can of course solve it optimally. Mm-hmm. Yeah, I think that's very interesting and somewhat related research. Actually, we will also see some lifting of states in this presentation. But
do you happen to know if you can always do that? Like, are there is it always possible as long as you identify the right nonlinear features, or are there systems for which you cannot do that?
That's an interesting question. I don't think that this is perfectly well understood yet. Like it is somewhat related to like Lasserre hierarchy ideas, where you know that if you add enough, as long as you add enough higher order polynomials to your state, then you can eventually actually globally solve. But but this number might be infinite. So for some problems, it's a finite number of higher order terms that we need to add, but for some problems it can be infinite. And I think, yeah, that's like a whole, that goes, I think, very soon deep into like math and like algebra theory and all of these kind of things.
Got it. Thanks.
No problem. All right. So when we all right, so coming back to the nonlinear cost function that I'm kind of considering here. So what could we even do to go from a locally optimal solver to a globally optimal solver? Just as a quick reminder, when we do local optimization, what we usually do is we start from some initial estimate, and then we approximate our function around that estimate, for instance, with a quadratic, like in Newton-based solvers, solve that to optimality to find the next iterate, and then we continue until we converge to a minimum, to a local minimum, where we don't go, where we can't further decrease the cost function. And here I like started at a good point, but of course, if you were to start somewhere else, then you would potentially converge to this saddle point, or you might converge to this local minimum, for instance. And I think it's like not obvious how we can even get around this, because I think often we think global optimality, in particular for non-convex problems, is just like very costly to obtain or impossible to obtain in like a reasonable time. So, and that is true to some extent, but yeah, I will try to convince you today that it's not always true. So for what we could do, and what people I think might be quite familiar with, is to try to get to global optimality. We could use a local solver, but we could, for instance, say we use a well-informed initial guess, and we could get that by, for instance, sampling the cost function to get a knowledge of roughly the cost landscape, and then start from a good point, or start from a good point based on the previous iteration, or something like this. We could also, like I mentioned earlier, we could say, as long as I'm below a certain cost, then I'm probably at the global minimum. Or we could just randomly initialize a few times and then pick the best out of all of these solutions. But although these are probably lead to better performance than just doing like kind of blind local optimization, they're still suboptimal solutions and not guaranteed to find you the global optimum. On the other hand of the spectrum, we do have globally optimal methods, and we could use those to find the global solution for sure. And for instance, with branch and bound kind of methods. But what the problem of these methods is that they're typically slow. Branch and bound is worst case exponential in complexity. So there are interesting works to speed these kind of solvers up and to actually make it tractable. But it does like remain relatively slow and hard to implement kind of solution. But there is something in the middle, and that's mostly what I want to talk about today, which is, can we still use a local solver, but then certify the solution that we get to? And that really means we run our solver once, and then we look at the local solution that we get. We run another kind of optimization problem that gives us this certificate. And the certificate either tells us that this is the globally optimal solution, or that it's not, or that it doesn't know. And in that case, we might have to start again and maybe start from a different initialization, for instance. And it turns out that this can be done very fast. and often we actually find the optimal solution relatively quickly. So this is an interesting trade-off between this like provably optimal methods and the only locally optimal methods. So this is the focus of today's talk. All right, this is the outline of the talk. And I will warn you that it will be relatively mathematical. So the size of the squares is like proportional roughly to the length of time that I will spend on each. And I really want to use this talk to try to demystify a little bit these like tools behind global optimality certificates. Because I think there can be kind of a high threshold to understand these methods and like read these papers and everything. But it's really not black magic what's happening there. So I want to really teach you how these tools work, and then hopefully that can help you to apply them for your own problems. And so I will go over the 4 main ingredients that are listed here, and I will go through them really like in detail one by one. So the first thing that we need to do, or that we need to realize, is that many problems that we work on can actually be lifted to a QCQP, QCQP being a quadratically constrained quadratic program. And in fact, by many problems, I mean, for us, at least, every problem we were interested in so far could be lifted to a QCQP. So if you have an original optimization problem like this one here, that's what I'm going to be kind of using throughout the presentation. F is our cost and theta is our unknown state. You can think about, for instance, positions over time all concatenated in one vector, or you could also have rotations there. And I think for pedagogical reasons, it's probably good if you think about f being just some polynomial function of degree k. And if you forget about adding constraints, but both of these assumptions are not necessary. In fact, we can also deal with, for instance, rational functions, or we can also add constraints, and I will show some examples of that later. But for now, I think it makes the math easier to understand, to not worry about these things. All right, so we can take this optimization problem and then introduce these lifted states to try to write it as in a quadratic form. And by lifted states, what I mean is that you take your original variable and you put it in a concatenated vector where you also add a 1, and you add all of these higher order polynomials. And so PD here means the polynomials of order D. And I combine all of these into what I call the lifting function G. And I say that the lifting function has, let's say, M elements in total. And the key is that you add enough of these lifting functions so that you can eventually write your cost as this quadratic form. And you can also write all of the lifting functions themselves as quadratic forms. So what that means, for the cost to be quadratic, you just have to go high enough in order. For instance, if it was a degree k polynomial, you have to go to k over 2 in degree. And for all of the constraints to be written in quadratic form, it means you shouldn't leave out too many of the polynomial of the degrees. So you should use kind of a complete lifting, like theta square, theta cube, and so on. And to make this a little bit clearer, I'm going to be using this toy example. This is a quartic polynomial cost function that has one global minimum, one local minimum, and a local maximum here. And in its most general form, you can write it like this. Now we introduce the lifted state vector, where we just have to add the square of theta. And then you can show that f of theta can actually be written exactly like this. And if you don't believe me that this is true, maybe you're familiar with the trace trick. So whenever you have a quadratic form like this, you can actually rewrite it as shown below here. This works because this is just a scalar. So you can, the trace of a scalar is equal to the scalar itself. And then once you have the trace, you can move around the arguments because the trace is rotation invariant. And so you move the X transpose to the other side here, and then you end up with this expression. And the trace of product of matrices is simply the pointwise multiplication. So the sum of the pointwise multiplication of them. So you can immediately convince yourself that here you just take like A0 times 1 plus 1/2 A1 times theta and so on, and you end up with the original cost function. I went through all of this because we will be using the trace trick again later. So if you weren't familiar with it, then now you have seen it at least once. Okay, and as I said, we want to do the same for the lifting functions that we introduced as well. So for instance, here we introduced G1 of theta equals theta square, and you can write that constraint also in a quadratic as shown here on the right. Okay, and we will be using also a sectic example, and that will become clear later why I also want to talk about this. I won't go through the math again, but you can do exactly the same and write it as a quadratic cost and with quadratic constraints. All right, so after we have done that, we can write an exactly equivalent problem to our original optimization problem, where now we basically drop the argument theta because we assume that these constraints are enough to kind of enforce the structure of our vector X. So this problem here is exactly equivalent to the original optimization problem. And so you might ask, okay, what have I gained? This is exactly the same hard problem to solve. But what is nice about QCQPs is that they actually enjoy quite a mature, like they are a widely researched topic, and they have there's a lot of mature duality theory that we can use for QCQPs. So once you have your problem in this very generic form, you can exploit all of these findings for QCQPs.
Hi, Frederike, I had a question.
Yeah, please.
Do the constraints make sure that in the lifted state X of theta, like the internal variables are consistent? For example, if P2 of theta is theta squared, then theta and theta squared should be linked somehow. Do the constraints make sure of this?
Yeah, so for all of these functions that we added, the constraints will make sure that they're consistent.
Okay. But
Thanks. We will see cases later where that's not the case anymore. But that's okay. I don't want to spoil it too much. But for now, yeah. For now, everything it's really perfectly equivalent. We have we can always enforce these kind of lifting functions with quadratic constraints because it's recursive. So if you have like a cube here, then you can constrain that using the square and the original one and so on.
Yeah.
Yeah.
Makes sense. Yeah. Thanks.
No problem. All right, so I say we can exploit duality theory, but I think many of you might not remember what duality theory is, or maybe you never heard about this because it's not so often covered in like grad school optimization classes. So I just want to give a brief reminder of what the dual problem is. You can always, when you have an optimization problem, you can always form what's called the Lagrange dual function. And this is, so G of lambda is the dual function, and it's really just the infimum, so think minimum of your Lagrangian, of your original cost, of your original problem, with respect to X. And you can show that because the Lagrangian is just an affine function in your dual variables, that this will always be a concave function, G of lambda. And then you can also show that if X is feasible, then this function will always be smaller than f of X for any X feasible. So the dual function always gives us a nice lower bound on our original problem. And in particular, when you talk about the dual problem, that just means we take our dual function and we maximize it over lambda. Then for the maximum, you also have that it's going to be smaller or equal to the minimum of the original problem. And just graphically, what that looks like is you have your original non-convex optimization problem. The dual function is this concave function here shown in orange. And the minimum here for f would q star would be here, and the maximum of g of lambda would be here. And you can see that in this case, there is a gap here that's called the duality gap, but we do have that d star is smaller or equal to q star. And in some cases, and in the cases that we're interested in mostly, you actually have a strong duality. And what that means is that the two functions perfectly touch here at their respective optimum. So you have that d star is equal to q star. And that's extremely powerful, because what that means is instead of minimizing this non-convex f of x, what you could do, for instance, is you instead maximize g, and you know that what you will find will be exactly the cost that your global minimum should have. So you can solve potentially much easier to solve problem, the dual problem, to know exactly what the optimal cost of your original problem should be. And this is not exactly what we will be doing, because we will see that there are many problems with this, like this can be too expensive to solve. But this is kind of the idea why the dual problem is so interesting. All right. So the second important, so building on that, the second important ingredient for global optimality is that the QCQP actually has duals that are semi-definite programs. And that's nice, because the QCQP, as I said, is generally hard to solve, and in particular, it's NP hard. And SDPs, on the other hand, can be solved in polynomial time. So that's kind of shows why this is interesting. All right, so I'm not going to derive kind of by hand why exactly the dual is an SDP, but I'm going to just show you what it looks like. So the Lagrangian dual, if you use the equation from the previous slide and just solve that, then you find that the dual problem is given by this problem here, where H is simply the sum of your original cost matrix plus these two terms, which correspond to the constraints. And there's an interesting fact that if you take the dual of the dual, this is also sometimes called the primal, then it's also an SDP, and it looks like this. And when you compare the primal problem with our original QCQP problem, then you can actually show that this is just a rank relaxation. So why is that true? Because if you just reformulate the QCQP using that trace trick that I told you about earlier, then you can rewrite each of these terms here as the trace of Q times the big matrix X, where X is X times X transpose. And you can write it, so this is perfectly equivalent to this problem here, where you have to include this rank constraint to make sure that you can factorize big X into small x times X transpose. And if you now compare this QCQP problem with the primal relaxation, you see that this is simply the same, but with the rank constraint dropped. All right. And what that means, so we have seen that the QCQP is our original nonlinear problem. The primal is a rank relaxation of that, and the dual is the dual of that. And so, yeah, the dual of the QCQP and the dual of the primal too. So in general, what we will have is that the function q, so the function value of the QCQP, q will be bigger than p, the primal function value, and that will be bigger than d, the dual function value. So you always have this kind of hierarchy of relaxations as shown here. And the third ingredient that we need is that, in fact, we often have strong duality. And for the primal versus the dual problem, this is relatively easy to see, because actually both are convex problems. And you can show that as long as you have certain constraint qualifications, you don't need to worry about what that means. But you can prove that you have strong duality between those two problems. And it turns out that for the QCQP versus its relaxations, you also often have a strong duality, meaning that, and this is equivalent to saying that this relaxation, this rank relaxation, is often tight. So even if we solve this problem, this primal relaxations, we will find a solution that actually has the correct rank. And so quite often we have this scenario here on the left, where all of the three things really intersect. And we can use that for many interesting globally optimal algorithms. And this is the fourth ingredient. So how can we use all these different formulations of the same problem? How can we use these to actually find global optimality? So we know that we could solve the QCQP, but then we will only get a locally optimal solution. So if you use, for instance, Gauss-Newton and get some estimate x star, where you might want to just solve f of theta, the very original problem that I'm not even showing here anymore, and then take your theta star and just lift it in the same way that we have lifted x here to get x star. So this is typically what you would do. And then this is a fast and memory efficient method typically, because there are very sophisticated iterative tools out there, because they have simply been used for a long time and optimized. But again, this is only going to be locally optimal. What you could now do, now that we have these relaxations, is you could also say, let's just solve the primal using some standard STP solver. And then I know that if X has rank 1, it's going to be globally optimal. And just as a reminder why that's the case, it's because we have really just relaxed the rank constraint here. And if you solve a relaxed problem and then find that the solution actually satisfies your original constraint that you relaxed, then you know that that's also the globally optimal solution of the original problem. It's like saying, I want to find the fastest way to get to work and also want to find a coffee shop along the way. Then if you relax the coffee shop constraint and you just find the fastest path, but it happens to have a coffee shop on the way too, then that is the fastest path with the coffee shop to work. Okay, exactly the same thing. And if the rank is not 1, then what you need to do is what's called rounding. So you need to project your solution to the set of matrices with rank 1. And that then you can be relatively far from the global optimum potentially, and it's not even a locally optimal solution anymore. It's just some estimate without any guarantees of how good this estimate would be.
So when we say that the solution is certifiable, certifiability is just a rank check of this matrix.
In this particular case, yes, but that's not what we will be using. I think, yeah, this is often not a great method to use. Yeah, exactly. So the certificate would be, does the matrix X have rank 1? If yes, then it's the global optimum. Yeah.
Does deviation from 1 indicate like any form of how suboptimal it is? Like, is 0.9 the same as 0.7? Or
Yeah, well, if you talk about, that's a good question. Yeah, if you talk about rank, it's usually you look at the eigenvalues and then you look at, so for rank 1, you want to know how big is the gap between your biggest eigenvalue and the next eigenvalue after that, the second largest. And
Okay.
of course, like if you solve this numerically, this will never be, your matrix will never be truly rank 1. So it will never, the second eigenvalue will never be exactly 0. So you
Okay.
have to look at the kind of relative difference, but that's actually yeah, that's not always easy to say when is the rank 1, like when is it rank 1 enough for me to say that it is rank 1.
Interesting. Okay.
Yeah, I will show an example of that actually in a few slides.
Yeah, thanks.
No problem. All right, and the other thing that you could do is so we saw that here it's not so nice that you end up with a solution that's potentially not even a locally optimal solution, and that if it doesn't have rank 1, it might not be a good estimate at all. So what you could do instead is solve the QCQP, and that gives you your X star and the Q star, so the value of your cost function. And then you also solve the dual, that gives you D star. And then if you see that D star is equal to Q star, you know that X, your estimate X star is actually the globally optimal estimate. And by the way, if it's not, then you don't know much, unless you know a priori that strong duality holds. But that's just a side note. All right, so let me just, this was like a lot of math. Let me just come back to the quartic example and show you these methods in action. So first of all, if we solve the QCQP locally, then of course, if we start, for instance, here, we would converge to this global minimum. If we start on the right here, we would converge to this local minimum. Now, if we solve the primal relaxation, so the STP in X, then what you find is that the eigenvalues of X in this case are as shown here. So the first one is 3 and the next one is very close to 0. So you can say that it has rank 1 probably, or it's at least very close to rank 1. And so you can extract from that your small x. You can use different versions. You don't need to worry about that. But whatever method you use to extract small x, you can show that they're all going to be very close to the true global minimum. So in this case, that's actually an interesting method. And the last one, we can solve the QCQP. That gives us this value here. So I'm just plotting the cost of that using the orange line. And then we can also solve the dual problem. So just as a reminder, the dual means that we're maximizing G of our Lagrange multipliers. And I'm just plotting G as a function of rho here. And here the blue line shows all of the feasible solutions. And if you take the maximum of all the feasible solutions, you end up exactly at the same cost as the primal cost. So from this, we also see that our primal, well, we would see that if we choose this minimum here, then we would have 0 duality gap. So we know that it's a global minimum. All right. So this looks fine. Like we have, at least we have some optimally or certifiably optimal methods now. But the problem with these SDPs is that they're typically quite slow and memory heavy to solve. And I need to mention here that there are a lot of people like looking into how to make this faster and how to solve especially low rank constrained SDPs. Like we know that X here has to have a low rank in the end. So you can make this SDP solver actually much faster using that knowledge. So that's an interesting direction of research too. But in general, if you're just using a standard STP solver, then these problems don't scale very well for like typical robotics problems. So the question is there a different way? Can we also certify it differently? And the answer is yes, we can. And we can call what I call here kind of the joint conditions. I didn't find a better word for those, but the idea is that you kind of combine the QCQP and its dual to generate these. You can think about these as kind of KKT conditions, and you can show that if you can find dual variables, sorry, I have to say, given a local estimate x hat, so that's locally optimal, that comes from our QCQP. If you can find dual variables rho hat and lambda hat, such that you have these two equations that hold. So this is the stationarity condition, and this is the dual feasibility condition. Then you know that x hat is the global minimum. And for some intuition, you can think about this problem to be almost like solving the dual problem, but you're helping the dual problem using the fact that you have this local estimate x hat. So you're helping find the dual variables by using this stationarity condition on x hat. And we can do that. So, and in fact, we can do that often really quite efficiently, because this first equation, if you have some, again, constraint qualification, which basically means that, for instance, your constraints are linearly independent, then you can show that this just has a unique solution. So you can solve for rho hat and lambda hat using the first equation, and then plug those into the second equation and see if your matrix is positive semi-definite. And then if it is, you know that you have that x hat is in fact the globally optimal solution. All right, so with this kind of with these joint conditions, what's nice is that we have we still have the really fast method because both the local solver and the certificate can be relatively fast. And at the same time, we can certify global optimality. And just showing this last method also in action. So using our QCQP estimates, we can solve for H and then look at the minimum eigenvalue of H. And we find in this case that here it's almost 0. And at this local minimum, it's minus 1.3, so clearly negative. So we can kind of conclude that this is the global minimum and this is only a local minimum. All right, and now, okay, the question is, does this always work? This looks too good to be true, kind of. Well, and this is now why I have also briefly introduced the sectic example. When we look at exactly the same methods for the sectic example, things don't look as clear anymore. You could argue that we still have an almost 0 eigenvalue, but it's not as close to 0 anymore as before. And in particular, if you look at the rank of X, it's the first 2 eigenvalues are now clearly positive. And also, if you look at the duality gap, there is a small but noticeable duality gap between your optimal solution, what we know should be the globally optimal solution, and the dual value. All right, so what happened here? And this is a little bit like coming back to the question of Abhishek in the very beginning of the presentation. We have enough constraints to kind of constrain our original small x, but in doing the rank relaxation, we may have introduced too much kind of wiggle room. So in the quartic example, everything was fine, because if you look at the matrix X times X transpose, what's shown in blue are the variables that are constrained by our original constraints, or the constraints in the QCQP. They're also called the moment constraints. And here everything is constrained because we also know that the matrix has to be symmetric. So yeah, we don't have to say, for instance, that this element is equal to this one. So everything is constrained. But in the sectic example, if you look at x times x transpose, we have constrained both theta square and theta cube, but we also have theta to the power of 4 here in this cross diagonal, and we can see that these two terms should be clearly the same, but nothing is actually constraining those. So this is a problem when you relax the constraint, and what you can do to solve that is to add what's called a redundant constraint. So this constraint is really enforcing that these two elements in my lifted variable should be equal. And they don't change the original problem. They're completely redundant for the original problem, but they will change kind of the tightness of the relaxed problem. And indeed, if we now revisit the example from before, but we have added the redundant constraint, then we see that now the eigenvalues. Sorry, I changed the order. That's confusing. Okay, but this is the primal problem. The eigenvalues are now such that X looks very much rank 1. Also, the duality gap has become 0. And if we look at our joint optimization, then we have like an almost 0 eigenvalue for H at the global minimum. And then at this point, the problem is unfeasible, meaning that there is no lambda, that there is no dual variables that satisfy both constraints. So we have made the relaxation tight, but this did make the joint method here much more expensive because, so just to explain what's happening here. So recall that for this joint method, we want to really find rho and lambda such that these two conditions are satisfied. But now this first stationarity condition doesn't actually have a unique solution anymore because we have added these redundant constraints in H, which means that LICQ doesn't hold anymore, and you can't simply solve for rho and lambda using this first equation. So what you need to do instead here is solve jointly for these two conditions. So this is like a kind of like a feasibility STP that you need to solve, or you can use a different kind of method like Douglas-Rutherford splitting, which finds the intersection of these two constrained sets. But so the take-home message is that redundant constraints actually make the problem significantly harder to solve. And that's something that there's still a lot of research to be done, I think, to understand how to deal with this problem. All right. Maybe before I go on, are there any questions about the theory part? And then I will go over some robotics examples using these tools.
Is the requirement of this redundant constraint coming from the way we constructed the lifted form, or is it always the case?
This is something that we don't fully understand yet. And I think in general, it's kind of an open research problem. Like it's almost an art, what kind of redundant constraints you need to add and how many are enough. But it does, I think in this case, it does come. So I think I'm sure we have never seen examples that are like only quartic, where we needed redundant constraints. But as soon as you have higher order terms in your original problem, then we have sometimes seen that you need redundant constraints.
And like you said,
yeah.
Sorry, go ahead.
Yeah, that's not. That's kind of like experience-based observation. I don't have like the mathematical proof.
Yeah, that's what I was going to ask is like, is there a formal way of coming up with these constraints? But it looks like not.
No, I think there is for sure, like in the math field, there are people working on this. Like there are principled ways to construct all of the possible redundant constraints given your problem.
Okay.
But they scale very poorly. Like if you add all of the redundant constraints, it scales really poorly. Here we only had it to add one, but if you have like higher orders, then you have to add like, I don't know if it's exponential, but you have to add like, or there are potentially many redundant constraints that you could add, and like finding which ones are truly necessary is like a little bit, can be a bit tedious, but very important for performance. So yeah, that's kind of an open research problem.
Interesting. It almost seems like problems that have a lot of high frequency terms somehow cause problems, which is just interesting because I guess even with the nonlinear optimization methods, if you have a lot of high frequency like X6 or X7, that you generally see jumping around quite a bit.
Yeah, that's true.
Yeah. Interesting.
Yeah, that's a good intuition. Yeah, there was another question in the room here.
Yeah, it was related to that one, but I guess a follow-up is, could you over-constrain the QCQP such that when you relax, you can't solve as well anymore? Or would that be considered like over-constrain, or like in this the case of redundant constraint? I guess it's kind of different from the redundant constraint, but more so like over-constraining your problem.
That's a good question. If you write the QCQP in this form, you can't really over-constrain add these redundant constraints now because they don't appear in the cost, because in the variable, sorry, because here x, small x really still only has one theta and theta square. Or in the static example, it would have one theta, theta square, and theta cube. It wouldn't have theta 4. So you can't actually constrain that. But oh, sorry. Oh, maybe you could. Sorry, I'm not 100% sure. But at least as soon as when you write it in the rank constraint case, then I guess you could add these. No, actually, you could probably add them here as well. Yeah, sorry, but they wouldn't change. They wouldn't change they wouldn't change the cost. So yeah. Okay, let me rephrase that. Yeah, yes, you can add them also in the QCQP. And in fact, I guess that's kind of what we do when we add them, because then when we look at the certificate, then we would have the redundant constraints in here as well. So yeah, that's actually what we're doing. We are constraining the QCQP more using redundant constraints, and they will not change the actual solution or objective value of the QCQP, but they will change the relaxations.
And then how easy it is to solve this relaxation.
Yeah.
Okay.
Yeah, but so I guess your question was if you can over constrain that too much. Was that also a question?
Yeah.
Yeah. Not sure. I think it just becomes more. It might become more harder and harder to solve. So like you want to ideally find the minimal set of redundant constraints that are necessary. Because if, for instance, you're solving the dual problem using also the redundant constraints, each redundant constraint increases the null space of your matrix. So it makes you're kind of relaxing the dual problem. So it makes it harder and harder. It might become harder and harder to solve the dual problem because you're giving it more and more freedom. So you want to, ideally find as few as possible, but just enough to make it tight. No problem.
I also have a question.
Yeah.
Is it always possible if you have given some non-convex QCQP, is it always possible to introduce enough redundant constraints to get a zero duality gap for the dual problem?
No, it's not always possible. I think so. I don't think it's always possible. I think it will be possible if I need to think for this is linked a little bit to Lasserre's hierarchy. I don't know if you ever heard about this, but so you can show that. Let me double. It's always these things are always tricky because you kind of hard. It's easy to say something. No, I think you might sometimes not be able to tighten the problem with enough with even like one of the redundant constraints. But yeah, maybe Connor, do you have
yeah, if it's a polynomial optimization problem, so if you can express the cost and the constraints in polynomials, then it's asymptotically possible to tighten the SDP. So it means you might have to add essentially the more redundant constraints you add, eventually it will tighten up, but it might be prohibitive to add all of the constraints. And you also have to change some of the formulation of the problem.
Yeah, thanks. And what I wanted to add also is that sometimes you can, if you can't tighten it, sometimes it actually helps to increase your state, even if your original problem was like a quartic problem, for instance, you can add more than up to second order variables in your X. And that means going up in the what's called the Lasserre hierarchy. So you'd add higher order terms that were actually necessary than were necessary for your original problem. And then eventually, and that might help you tighten the relaxation. But then for each degree that you go higher, you also have to add, you might have to add all the redundant constraints that go with that higher degree. And then it can become very expensive to solve. But there are some like very interesting theoretical results by Lasserre that say that for many problems, like increasing the order, you will actually get to a tight relaxation with a finite order. But again, that might, for some problems, you have to go infinitely high in order. So you can't actually tighten the constraint with a finite order. Yeah. Does that answer your question?
Yeah, it's like and I guess it's not an ideal state of affairs, but that's to be expected. Yeah. We can't solve everything perfectly.
Yeah, because if it was always possible, then I guess you kind of violate the NP hardness of the original problem. Like the whole thing.
Right, yeah, there's no way it could be like always convexifiable, let's say.
Yeah, exactly. All right, but again, for many problems, it actually turns out that we have strong duality, even for low orders, few redundant constraints, and also, and that's in particular the case when you have reasonable noise in your problem. But I will talk a bit about that later.
Wait, actually, sorry, it's just like a really quick follow-up. Can I is there like a physical interpretation that I can say like secretly these problems are like hiding a convex or concave structure within them? Like, because you say like, well, I bring this up only because I saw like a offhand remark that I didn't think about geometrically, which is like, in the like single constraint QCQP case, like the trust region problem that's like famously has like zero, like strong duality holds. Like someone made a remark that it's like actually just like, it's just like pretending to be non-convex and there's actually just like convex structure in there. Like, can I interpret these other problems that way, or is that like only a trick of the math and I like shouldn't look for like geometric or like physical meaning?
Guys, as we're a little bit over time, is it okay if we postpone some questions to the end?
Yeah, we can talk about this later.
Or you guys can also take it offline. I'm sorry for that, just to be mindful of the time.
No, yeah, thank you. I totally lost track of time, I think. Yeah, thank you for all the good questions. But yeah, let's discuss this later, Adam. Yeah. I think that, these cost functions are truly non-convex. I think they're not like these, benign cost functions that actually end up not being convex, not being hard to solve. I think these are like the problems that I'm looking at here are truly non-convex and have local minima, but that we can still solve them. All right. So, all right, so then let's just look at some problems in robotics that we have solved using this method. And again, this section will be relatively short, and I will mostly refer to the papers that we have recently published on these topics. So in general, so what I want to do is kind of fill in this table bit by bit. So I will be talking about 3 robotics problems. The first one being robust line fitting, then landmark SLAM and range-only localization. And we can always kind of think about or describe the problems by what was the original problem that we were trying to solve in terms of variables and cost. Were there constraints in the original problem, and what local solver can you use to solve it? And then look at how the certificate works. So the robust line fitting paper, this is an archive paper that's mostly for, has like a pedagogical value. It's a tutorial style paper to understand, in particular, redundant constraints. So just a very quick overview, what we're trying to do is we have some data points and we want to fit a line to these points. And we are interested in the problem where you might have outliers. So you might have points that are not at all on this subspace that we're trying to fit. So what you can do for these kind of problems, this is like a classic robust estimation problem. You can, so we want to estimate 3 or yeah, we can parameterize the line with 3 values in the plane. Then we can use a robust cost function, and we can we have actually a constraint for this particular parameterization, which says that the normal vector is of length 1. That's because we chose a particular line representation. And then what you can do is you can solve this robust cost function iteratively using, for instance, reweighted least squares. So this would be our local solver that we want to certify. And I won't go into too much detail. Again, this is quite explained quite in detail in the archive paper. You can lift the problem by introducing these kind of vectors here. And then our constraints will basically be that these vectors have to be parallel. And the intuition here is that we are saying that all of the vectors, so every Qn has to be parallel to Q0. And it turns out that you also have to add the redundant constraint that every Qn has to be parallel to every Qm as well. So these are all constraints that were not like that are completely redundant, because if one vector is parallel to all others, then they're all parallel to each other. But it is necessary to tighten the relaxation. And because of that, you have to use a joint method for the certificate. And in this case, we use Douglas-Rutchford splitting. And again, you can see the paper for how exactly that works. That's actually quite a neat method to solve these kind of problems. All right. And here's what the results look like. This is a failure or like a correctly a certifiably optimal solution here on the left. So we have a line that's fitted to these points and correctly ignores the outliers here. So in green is the STP solution, so the primal solution. And the pink one is overlaid. You don't see it. It's exactly under the green line here. And this is very close to the ground truth. So here our local solver found the global optimum, and we can certify that. And on the right-hand side, we have a case where the local solver incorrectly fitted to the outliers here. And we can also, in this case, the certificate would not hold. So we can, in this case, we know that, or we can at least say that we don't know if this is a global optimum. And often it means that it's not a global optimum. All right, that's very like briefly what this first method is about. And I will talk a little bit in more depth about the other 2 methods. The first one being certifying landmark-based SLAM. So this is work that was done by Connor Holmes from the lab, mostly before I arrived here, but I do want to talk about it for the sake of completeness, and I think because it's a very interesting method. So the method in a nutshell is really trying to solve a classic SLAM problem, where this is the factor graph representation. You have in black kind of the robot that's moving along a trajectory. At each point, you can parameterize its pose with the rotation and the translation. And from time to time, it's measuring landmarks. So it's seeing landmarks that I denote by M here. And the measurement model is a linear one. So if you look at the factors here between the poses and the landmarks, then they will have this form, which is a standard linear measurement form for landmark measurements, like what you would see in LiDAR as well, for instance. And between the poses, we also can add these relative measurements where we have some knowledge of the relative rotation and translation. And then what we want to solve is this standard map problem, where we want to minimize the sum of all of these cost terms. And with respect to, like, quite importantly, that the rotations here have to be in the special orthogonal group. So this is a case where the original problem, again, is a constraint problem. But you can actually quite safely, so SO3 means it has to be R transpose R is 1, is identity, and it has to have determinant 1 plus 1. You can actually safely relax the determinant condition, and it will still give you can still solve. So this is, you can relax that easily to a QCQP, and you don't need to any lifting because the cost was already quadratic as well. So then for this local solver, you can use efficient sparse Gauss-Newton solvers using like D group algebra, so that you can so you ensure that your rotations actually lie on this manifold of SO3. And what's a core contribution of the paper is that you can exploit the sparsity of Q and H in particular to also make sure that the certification is very efficient as well. So as efficient as the local solver. And this is just a brief, a quick example of how this method performs. This is on a real data set, a handheld stereo camera data set. And you can see that and on the left is a global minimum, on the right is a local minimum. And you can see that the local minimum is indeed quite far from the ground truth here. And the certificate allows to detect that. So here on the left, the certificate would hold, and on the right, it doesn't hold. And I only want to discuss this very briefly. Again, yeah, we don't have time to go into too much detail, but this work kind of built on a lot of work that came originally from the computer vision literature, like and their landmarks are often kind of marginalized out. People use them mostly to get relative transforms and don't truly treat them as landmark measurements. And similarly, this in the paper SE Sync, which is the most related, I think, to the proposed, the landmarks are kind of just treated as degenerate poses. And we don't do that, or Connor doesn't do that, but uses really treats them as landmarks without a rotation in particular, and that has great efficiency gains. And also the second line of research and a lot of the research in that direction actually looks at different solvers. So not using a local solver like we do, but using, for instance, Riemannian descent and the Riemannian staircase. So instead we use standard solvers always, which is nice because then you can use these classic solvers from robotics. But of course, it's also interesting to see like development in these more efficient Riemannian descent kind of solvers. All right, and now the last thing that I want to talk about is the range-only localization problem. And I will go a bit fast just so that we have enough time. So again, the factor graph representation of this is very similar to the previous one, but now instead of, so we again have a robot on a trajectory, but now we have, instead of odometry measurements, we actually use a motion prior to have like temporal consistency. And the distance, the measurements to the landmarks are now distance measurements. And so in this case, the original problem is quartic because of these distance measurements, but we can make it QCQP by introducing substitution, of which is basically the norm of the position squared. And then again, we can use a nice sparse Gauss-Newton solver as our local solver that in particular leads in this case to a GP Gaussian process solution that we can also use to interpolate between states. And in this particular case, also, again, it's very sparse. The problem structure is very sparse, and we can use that to certify very efficiently. But in this case, standard off-the-shelf solvers have problems certifying. So we have a custom LDL decomposition method that's equally fast and also so as fast as the local solver. All right, I will jump over this. It's not, but we'll go directly to the real result. So this is exactly the result that I've shown you in the very beginning of the presentation. And I just wanted to give you one more insight, which is, again, what I mentioned. You can see here the cost of the optimal solutions versus the RMSE for different trials in different colors. And you can see, for instance, if we look at the orange one, which is the one shown on the left, the global optimum is here on the left with quite a low RMSE. And the local optima have very high RMSE, but almost the same total cost. So the cost would be really a poor, kind of a poor indicator of whether you find the global or local optimum. And instead our certificate detects these cases successfully. All right, and I will jump over this because I think we don't have time, but happy to talk about how this compares to related work after the presentation. And I just want to take a few minutes to go over the discussion and kind of what I think are interesting problems to solve in the future. So first of all, we have seen that for many of the problems that we typically solve, they are originally or generally hard to solve, but they can actually often be solved to global optimality in polynomial time. And in particular, we have seen that a local solver will actually often find the global optimum, at least in the problems that we have been looking at. So we can exploit these like efficient and mature iterative solvers and then just add the certificate as an add-on. And that way we know exactly when we find the global optimum and when we don't. And so in general, I think I hope that I have convinced you that global optimality seems to actually become a realistic goal for many applications in robotics. And again, I've only mostly talked about state estimation, but I think there are also great potentials in other robotics problems. And that brings me to the last slide. So for the open research problems, I think one very interesting question to answer is when we know that strong duality holds kind of a priori. Because for now, we often see in hindsight that it holds, but it would be great to know beforehand. And maybe we could even influence our problem instance to make sure it holds. So for instance, place anchors in a certain way so that we know that we will have strong duality. And then I already mentioned that dealing efficiently with redundant constraints is very important, knowing which redundant constraints are necessary and how to speed up these solvers for finding the multipliers under redundant constraints. And then finally, I think it's quite a promising or like quite a fun research direction to also incorporate inequality constraints, because then you could do things like if you're going around an obstacle, you typically have these homotopy classes that are basically equivalent to two different minima, one being in this case the global and one the local minimum. So if you can certify those, that would be kind of an interesting research direction, I think. Right, so with that, thank you so much for listening. Feel free to reach out to me. And just one quick note, we are planning or hoping to organize an IROS workshop about these topics. So if you're interested, please keep an eye out and join. The goal is to really make it very accessible and try to like teach these tools to the broader research community. Thank you very much, and I'm happy to take any questions from here.
Thanks, Frederike, for this wonderful talk. And it's now the QA time. Any questions from the audience? Please just unmute yourself and ask.
Yeah, we have one here.
Yeah, so thanks. That was really insightful. So I was wondering if you could give any like insight into what you actually do if you detect a suboptimal problem. So that's always kind of something that's been on my mind. It's like, okay, great. I now know that my optimization didn't converge to the global minimum. Like, are there, I guess, is there a field of literature on how to, like, what to do past that point?
Mm-hmm. Yeah, there is actually. So what we have been doing, or what I've been doing mostly, is randomly initialize again, and most times it will actually find the global optimum. But there might be cases where that doesn't work, and then there are methods that also exploit Lagrangian duality to kind of try to figure out what's a good direction to go in if you are at a local minimum. Yeah,
so you can actually leverage your, I guess, like your optimality check to inform the next step. Okay, that's cool.
Exactly.
Cool, thanks.
No problem.
So I have a question. So I'm mostly working on computer vision. So we have deep neural network, which is like so deep neural network training is like a super high dimension optimization progress, right? And usually it's almost impossible to find the global minimal, but people usually find out that global minimal can also work quite well. So I'm just curious, in the problems you mentioned, they are relatively lower dimension compared to deep neural network, right? So in these cases, what is so from a downstream application or an, I don't know, outcome perspective, how much difference will a global minimal and local minimal make to the final result, or to the to the final outcome of the Simpson or something?
Yeah, that's a very good question. I think if you can globally certify your like neural network training, I think you will become a millionaire or something. Yeah. I think that's definitely that's currently, I think, out of reach with like these millions of parameters or thousands of parameters that you have. I think that's pretty hard to do, but yeah, regarding performance of local versus global minimum, I think that's like a little bit of I guess comes up a lot nowadays, that like in machine learning, you do all these things that are like not optimal, and like you have all these approximate solutions that actually end up working really well in practice. So do we even need global optimality there? And so I think that's like a question that deserves consideration. I think that's maybe in certain use cases you actually really care about optimality. Like for safety critical use cases where you really want to be sure that you're not at a bad local minimum, but at the global minimum. And I think I could see that in machine learning, that's also often like necessary, or like also sometimes necessary. And there is like work in that direction, right? With like trying like provably safe learning and like Lipschitz constants of networks and all these research directions. I think it's somehow, because learning is like by design like suboptimal, or like it's kind of hard to make any claims on optimality because you don't really have a model. And I think by nature these problems are tackled differently. Like when you talk about these safe networks, it's more about how like the Lipschitz constant of the network, and like how much like changes in your input will change the output. So it's like a different kind of, I think it's it asks for different kinds of methods because the nature is different. But I think it would be super interesting to actually try and see how much from one field can actually help the other field. And if you could somehow bring Lagrangian duality to neural networks, or yeah, I think that would be really interesting. If anyone knows about work in that area, I would be very interested. But I haven't personally heard about anything. That's a very fuzzy answer, but yeah, I hope that helps.
Very insightful. Yeah, I haven't think about this problem in the past because I always feel like just apply some stochastic gradient descent, and if the model converge, then it usually works very well. But as you said, from a certifiable or safety constraint environment, then yeah, probably we do need some kind of optimal constraint.
Yeah. Yeah. Thanks for the question.
Any other questions? Okay. If we don't have more questions, I guess we can stop here, and let's thank again for this great talk.